Hello, this lecture is on truth tables for logical operators or logical connectives. So far we've seen what the dot and the wedge, the horseshoe, what those logical connectives can be used to translate. The dot can be used to translate the English word and, for example. The wedge can be used to translate the English word or, for example. But we haven't seen what the dot, the wedge, the horseshoe, the biconditional, and the tilde mean. They don't mean their English counterparts. So, for example, the dot does not mean and. The reason that we do this, that we define the logical connectives in a way that is separated from the English, is because English can be so ambiguous, and we want our language to be unambiguous. In addition, the dot can be used to translate not only and, it can use to be translate but, and those have different meanings. So, yeah, we're going to give a truth table definition for our logical connectives. So the negation is easy. The truth table definition for negation shows that for any statement P, remember that P is a statement variable, not P will have the opposite truth value. So here's our truth table. We have the truth table for not P. Not P appears in the top right corner. P appears in the top left. In the bottom left is every possible truth value for P, which ends up just being 2, TF. And the bottom right is the output. So whenever P is true, the output for not P is false. Whenever P is false, the output for not P is true. This means that basically the negation flips the truth value of the statement it negates. And this is intuitive. This is how the not works in the English. So we have the statement CSN is a public institution. Suppose that's true. It is true. We could represent that by A. Now negate that with a tilde A. Or with the English, it is not the case that CSN is a public institution. When you add the negation, it flips the truth value from true to false. And if CSN, we say it was a private institution, then CSN is a public institution would be false, and the negation would flip that to true. So negation is easy to remember, it's intuitive. So is the conjunction, though the conjunction gets a little more complicated. Before moving on to conjunction, I want to show you how to construct a truth table for a compound statement that has more than one component statement. So as an example, we have P.Q. This is a compound statement, P.Q, that has more than one component statement. The component statements being P and Q. So what you should do with a compound statement that has more than one component statement is list each component statement on the top left of the table in the order in which they appear in the compound statement from left to right. So in our compound statement P.Q, P is first, Q appears second. So on the left top side of the table, we list P first and Q second. So the component statements must be listed in the top left of the table in the order in which they appear in the compound statement. And then, of course, the compound statement goes in the top right. Now we can list all the possible combinations of truth values for P, Q. We'll do that in the bottom left. So how do you figure out how many combinations there are for a given compound statement? Well, you calculate 2 to the power of the number of component statements there are. So in P.Q we have 2 component statements, P and Q. So we list P first because it appears first in the statement, and then Q because it appears second in the statement. So we have 2 component statements. So we calculate 2 to the power of the number of component statements. So it ends up being 2. 2 to the power of 2 is 4. So that means there are 4 possible combinations of truth values for P, Q. So we have 1, 2, 3, 4. Row 1 gives one possibility when both P and Q are true. Row 2 gives another possibility when P is true and Q is false. Row 3 gives another possibility when P is false and Q is true. And finally, row 4 gives another possibility when P is false and Q is false. Now, a way to figure out that you've gotten all the possible combinations is, well, first you do this calculation, and then you just, list on the first column closest to this bar, you list, starting with true, you alternate true, false, starting with true. So you start with true and you alternate by 1. True, false, true, false. So you're alternating after every row. For the column next to it, you alternate true, false, starting with true, by 2s. So you list true twice, false twice. If you had a third row here, you would alternate by 4s. True, 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 true. You'd only have a third row if you have an additional component statement. Okay, and then here you're going to list all the outputs. Alright, so that's how you create a truth table for a compound statement with more than one component statement. You have the component statements here, you have the compound statement here, you have the possible combinations of truth values for the component statements here, and you have the outputs here. So the outputs would be like, whenever P is true and Q is true, what does that make the whole statement P dot Q? Whenever P is true and Q is false, what does that make the whole statement P dot Q? Whenever P is false and Q is true, what does that make this whole statement? Is it true, false? Whenever P is false and Q is false, what does that make this statement? Is it true, is it false? Now, I want you, when you construct a truth table, to list it just as I have here, where you're listing true, false, and then true, true, false, false, so that we have a standard way of creating truth tables. Now here's the truth table for conjunction. We've seen the truth table for negation. The truth table definition for conjunction shows that for any combination of truth values for P, Q, P dot Q will have the following truth values. Whenever P and Q are true, P dot Q is true. Whenever P is true and Q is false, P dot Q is false. Whenever P is false and Q is true, P dot Q is false. Whenever P is false and Q is false, P dot Q is false. Now this is very intuitive. It's the way we understand AND statements in English. Consider this AND statement. Today is Monday and it is raining outside. Suppose that they're both true. It's Monday, here, P, and it's raining outside, Q. Well, doesn't that make the whole statement true? If your friend came up to you and said, hey, it's Monday and it's raining outside, and you're like, yeah, it is Monday, yep, it's raining outside, you would judge that what your friend said was true. But if your friend said it's Monday and it's raining outside, and it was true that it was Monday, but false that it was raining outside, say it was completely sunny, you would judge that his entire statement is false. Of course, one part of his statement is true, but the entire statement itself is false. So if he said, hey, today's Monday and it's raining outside, and you looked and it was sunny, you would say, no, what you said is false. I mean, if you're a good friend, you probably wouldn't put it that way, but yeah, logically it's false. Now what if he says, today is Monday and it's raining outside, and it's actually Tuesday, so P is false, and it is raining outside? Well, the whole thing is false. And if it's Tuesday and it's sunny, the whole thing is false. So it's very intuitive here. And note that the only time that a conjunction is true is when both conjuncts come out true. That's an easy way to remember the truth table. So the way you remember the negation is that the negation flips the truth value of the statement it's negating. And then the way to remember a conjunction is just this. Whenever both conjuncts are true, the whole thing is true, and otherwise it's false. Then we have disjunction. The truth table for definition for inclusive disjunction, I'll explain to you on the next slide what an inclusive disjunction is, shows that for any combination of truth values P, Q, P wedge Q will have the following truth values. Whenever P is true and Q is true, the whole thing comes out true. P wedge Q, this whole thing is true. Whenever P is true and Q is false, the whole thing comes out true. So the statement P wedge Q is true. Whenever P is false and Q is true, the whole thing comes out true. And whenever P is false and Q is false, the whole thing is false. Now, so this means that the only time a disjunction is false is when each disjunct is false. Every other time it's true, so that's an easy way to remember it. The disjunction is false whenever both disjuncts are false, and it's true every other time. So this one isn't as intuitive, I think, and I'll talk to you about that. Because, you know, if someone says today is Monday or it's raining outside, you might think that if both of them are true, then this statement is false. If they said, you know, today, either today's Monday or it's raining outside, and you know, if it ended up that it was Monday and it was raining outside, you would say, well, like, looks like you said something false. Yeah, so this one is a little bit counterintuitive. That's because there are two notions of disjunctions. One is inclusive, one is exclusive. So an inclusive disjunction, both disjuncts can be true at the same time while the whole statement is true. Both disjuncts can be true at the same time while the whole statement is true. That's the way we've defined this disjunction here as inclusive. Both statements can be true at the same time while the whole statement is true. The exclusive disjunction says that both disjuncts cannot be true at the same time while the whole statement is true. So this says if both are true, the whole thing comes out false. Our wedge, our logical operator wedge, is defined as an inclusive disjunction. Here I'll defend our truth table definition for the wedge. You know, I'll admit some uses of or in English are inclusive and some uses are exclusive. So here's an inclusive use of or. Passports will be issued only to persons who were born in the country or who are married to natives of the country. And famous logician, philosopher Quine said this. He gave this as an example of inclusive disjunction. All right, so suppose someone's going to get a passport and they satisfy both conditions. They were born in the country and they're married to a native of the country. They're not going to be denied a passport. This is inclusive. So if you satisfy both conditions, you still qualify for a passport. So when it says or there in that statement, it doesn't say you can only satisfy one of them in order to get a passport. If you satisfy both, you can get a passport, so it's inclusive. But some uses are exclusive, like when the server at your favorite restaurant says, do you want the soup or the salad? What they mean there is, do you want the soup or the salad, but not both? They mean that they're giving you one choice. You want the soup, and if you choose the soup, you can't have the salad. Or do you want the salad, and if you choose the salad, you can't have the soup, unless you pay more. The only other option would be you could say, well, I want both, and I'll pay the extra that it takes to get both. So like if a meal comes with a soup or a salad, they're offering you one or the other and not both, unless you pay more. So that is an exclusive. Use of the or there, whereas the top one is inclusive. So here's the thing. in English, both senses of or are there. In propositional logic, if we define the wedge as inclusive, we can still express exclusive disjunction. It's there below. M or W and not the case that M and W. That is exclusive disjunction. So we haven't lost anything by defining our or as inclusive. By defining our or as inclusive, we haven't lost anything because we can capture both senses, the inclusive and the exclusive, by using propositional logic. That is the first half of our definition of our logical operators. The second half is coming.